Hello everyone, welcome to this video's edition of numerical analysis. And today we're going to talk about solutions to equations in one variable. That is, we're going to talk deeper in bisection, Newton-Raphson method, and the secant method. So without any further ado, let's get into it. So what is bisection? Basically, this method is based on the intermediate value theorem and generates a sequence of approximate solutions to f of x equal to 0 that converge to a root of f, provided that f is continuous on the interval where we believe a root exists. So this is all fancy mumbo jumbo, and if you can understand this, great, but I believe that it's basically important to be able to understand it graphically and conceptually rather than having you know, the definitions for them. But essentially, when you're given a function f that is continuous on a comma b, where a solution to f of x equal to 0 is expected to exist, then the bisection method begins with finding the function of values at the endpoints, namely f of a and f of b, and if this function of values change sign, then we know that the graph will cross the x-axis at least once on the interval a comma b. That is, f of x equal to 0 will have at least one solution on the interval, then the bisection process can actually begin. So let me just break this statement down for you, and hopefully you get a little bit more context about this. So what this entire statement here is talking about, especially starting from here, if this function values change sign, means that we're looking for something that we call in numerical analysis uniqueness of a root. So the uniqueness of a root implies that, or it tells that, if we have a function and we place in our endpoints, let's just say f of a and f of b, right? If we plug in our endpoints into f of x, if the values of f of a and f of b are opposite signs, then there exists a zero or a root within that function where a root exists, basically uniqueness of a root. We're trying to see if the function crosses the x-axis at least once within that interval. And that can be used to solve for solutions to equations in one variable. And that is a very important concept that we need to learn and we need to understand. And we're going to go through this in detail within the video. But for now, just have this concept noted down and you make sure you have a general grasp of this type of concept. Alright, so let's say you have a function f of x equals to the square root of 2, right? So let's make f of x such that x is subject to a formula. So unlike what we did in our first video in our introduction to numerical analysis, here we're just going to go straight into the actual solving process rather than you know, um, finding f of x and all that. So we have the square root of 2 is equal to x, and then we are going to um, add a radical of 2 to both sides, right? So we are getting rid of this guy here. And when you say 2, the square root of 2 to the power 2, that's basically just 2 because the radix here gets rid of the radical there. And then here we have x to the power 2. And if we were to add negative 2 on both sides of the equation, we are going to say that this negative 2 plus 2 equals to 0, and then x squared minus 2 is just x squared minus 2. And then we have our f of x, which is equal to 0. And then we have our equation. Okay, great. So now that we have our equation, next we have to find arbitrary values within the function to be able to find our interval. Right, so finite interval is a function that can exist. That is, we show that f of x has a unique root within the interval you have chosen. Great. So now we choose our arbitrary values for our interval. Let's just say we have test 1. It's important for you to be able to get values that are closer to 0 or very close to each other to avoid issues of complications later on down the line, because you might get inaccuracies and also you might get you might make your work as as hectic as possible anyway. So let's just say our test run is 0 and 1, right? Something simple. And then we plug in 0 in f of x, and f of 0 is going to be negative 2, f of 1 is going to be negative 1. Notice that when we plug in our values here, um, as we increase the number, or um, as we increase our number, sorry, to the positive infinity side, we are going to increase the number of f of x going positive as well. This is due to the property of the square root of the function here. So the higher you increase this guy here, it will just keep on increasing towards the positive, because any number in a square, any number that is squared is positive. So long as the values here keep on increasing, this equation will also keep on increasing. But this is not our equation, because negative 2 and negative 1 are both negative. So meaning this is our wrong equation. But we can get a value of 1, because it is closer to 0, or it is closer to a positive value than 0 is. So we're just going to say our new arbitrary value is going to be 1, 2. And if we plug in 2 into f of x, we're going to get 4 minus 2, which is 2. Now this is the actual correct interval, because we have negative 1 and 2, and these two are completely polar opposite signs, and that satisfies the condition of a uniqueness of a root. So if we have our interval 1, 2, it means that f of x crosses 0 at least at one point. At one point within this interval 1, 2, we have a 0 0.5, maybe you can have 0 0.4, 0 0.3. I'm not really sure what value it is, but at some point between 1 and 2, there is a value that when you plug it into f of x, it will give you exactly 0. That's what uniqueness of the root actually means. Okay, so now that the interval has been found, let's find the midpoint within the interval where the bisection process can begin. So how to find the midpoint of the interval? We're going to say m for midpoint is equal to b plus a divided by 2. This is your formula to use to find the midpoint. And in this case, we have our interval, which is 1, 2, and we're just going to plug in the values there, and we get 1.5. And if we have 1.5 there, then we can find f of m, right? So meaning we find this value here, and then we plug it into our f of x, and then we get our value of 0.25. Great. So now that the midpoint has been found, let's find the number of times we need to repeat this action to have the desired accuracy. And for you to find the tolerance, you can use this formula right over here. Or if you have been given the tolerance, but you don't know how many times you need to find the approximate or to the tolerance, you can use this formula, which is n, which is greater than or equal to log b minus a minus log tolerance divided by log 2, right? So let's just say our tolerance is equal to 10 to the power negative 3, and if you plug in the values right in here, if you can use your calculator, use the calculator, you have n, which is greater than or equal to 9.9657, which is approximately 10. So just to recap everything that we've talked about here, you have this formula. This is the formula to use to find the number of times you need to repeat this action over and over again. So this is the number of times, which is n. But it's very rare for them to not give you a tolerance. But if you've not been given a tolerance and you've been asked to say, hey, find the, or you've been given the value of times that you have to do this, then finding a tolerance, you just use this formula. And if you plug in this exact equation in your calculator, you will get a value of 9.96, well, which is approximately 10. Okay, so now we have our values. Let's get into it. So we have our tables here. We have 1, we have 2, we got 1.5, we got 0.2, right? Great. So now, because this guy is positive here, we are going to say um, this value comes um, B, on the B interval there. M becomes B, and then A becomes 1. So I'm going to explain to you exactly how this goes, and right now just try to understand this and try to follow me here. So let's start this whole iteration first. So this is our initial values that we found, right? We found our interval, which is 1, 2, and then we found our midpoint, which is 1.5, and then we found our f of m, which is 0.25. But then if f of m is positive, then our m value becomes b, right? Because we have now cut the interval um, a point 0.5 less than what we actually needed. So basically, bisection, we are cutting down the function so that we find the exact point within the function where that value actually is. So we're cutting down in this point. So notice that we've cut down from 2, we've gone to 0.5, sorry, 1.5, because here we have our midpoint, which is 1.25, right? So if our b is 1.5, then we can say that our new interval is 1, 1.5. And if you were to add that together, we are going to get 1.25 here. 1.5 plus 1 plus 1 divided by 2 will give us 1.25. And f of 1.25 is going to be equals to negative 0.4375, and then we plug it there. So if this value is negative, then the value that we have here becomes a, and then this value remains the same. So we have this type of rule that we have. So if f of m, which is this guy, is greater than 0, meaning if it's positive for our case here, then b is equal to m for the new interval a comma b. So meaning for this new interval, this value will equal to this value, right? But then if f of m is negative, right, for this function, then a is equal to m for the interval a comma b. And then, as we have noticed here, this guy will become 1.25, like so. So we have 1.25 and 1.5. And then when you add these two together and then divide by 2, finding the midpoint, you get 1.375. And then when you find f of 1.375, you get a negative. And then so on and so forth and so on and so forth. So you just keep on doing the same things, minding this rule that's there, following the midpoint theory. So basically here we're just looking at midpoint f of m, midpoint f of m, midpoint f of m, midpoint f of m. And this midpoint is where we actually get our approximate value for as many times as we were told. So like I said, our iterations start from 0. X naught means the first iteration. So we could start from n naught, which is 0, and then n9, which is basically just the 10th iteration that's there. So if you follow what I've just said for finding m, the midpoint, and then f of m, you are going to get this type of relationship. So for the 4th, for the 5th, for the 6th, for the 7th, for the 8th, for the 9th, and so on and so forth. Notice that as we get to the 7th iteration, you have 1.41406. This becomes arbitrarily close to our actual value of the square root of 2. Because if you plug in the square root of 2, you'll get something as close and as similar to this. And as you keep going and going and going, your values will gradually keep on getting closer and closer to their actual value. So I hope this is a general idea of how bisection works. So first things first, you are going to find your initial interval, which is 1, comma 2. And then you're going to find the midpoint, which is 1 plus 2 divided by 2, which is 1.5. And then you're going to find the f of the midpoint, which is 0.25, right? So the rules are, if the function of m here, or f of m, is greater than 0, if this guy is positive, then this 1.5 becomes b, and then your new interval becomes 1 and 1.5, right? Good. And then you repeat the same process by finding the midpoint and then finding f of the midpoint. And then if this value is negative, then the value that you have here becomes a, and then 1.25 plus 1.5 divided by 2 will give you 1.375, and then f of 1.375 will give you a negative value, and then if this is negative, then this value becomes a, and so on and so forth, and you kind of get the relationship that's there, right? So with that being said, that's done with bisection. So we go to Newton-Raphson's method. So now we have a concept called Newton-Raphson's method, and this basically is derived from the first Taylor polynomial. And the condition is, as long as the function of f is twice continuously differentiable on the interval a, b, and has an approximation of p naught, which is a member of that particular interval a, b, to the solution p, such that the derivative, or the first derivative of p naught is equal to, or is not equal to 0. Again, this is all fancy mumbo jumbo, so let me have give you a clearer definition of what this is. So let's just say we want to find Pn plus 1, right? Oh, this is the formula, by the way, to find Newton-Raphson's method. And you have Pn plus 1, which approximates Pn minus f of Pn divided by the first derivative of f of Pn, right? So this is our function. So to be able to understand our earlier description, let's have an example to actually show you what I mean. So let's have an equation, f of x is equals to x cubed minus 4x squared plus 1, right? First, we need to find out if a unique root exists in this function. Basically, we want to find out if a 0 exists within this function. So we find the interval for this function, right? So let's have the interval 0, 1 as our initial test. We have f of 0, which is equal to 1, and then we have f of 1, which is equal to negative 2. Great. So we do have our interval, right? Because f of 0 has got 1, which is positive, and f of 1 is negative 2. So these two values are polar opposites, and if they are opposites, then it means that this function crosses 0 at least once within the interval 0, 1. Great. Now that we have our interval, we can find the initial value within the interval and call it our x naught. So let's say x naught is equal to 0.5 within our interval 0 and 1. We can use the formula, this guy here, to say p of m plus 1, which is equal to, which approximates Pn minus f of Pn minus the first derivative of Pn, right? So in this case, our Pn could be xn, and I'll be using this interchangeably, so don't get confused between the two. So if we're looking for our first term, right? We're looking for our first term, so we are going to say P1 is going to be P naught minus f of P naught divided by the first derivative of P naught. So if we have our Pn, which is 0.5, and then, like I said, Pn and xn, we're going to use them interchangeably. So if our P naught is equal to 0.5, then we have 0.5 here, minus f of 0.5 divided by f prime of 0.5. So meaning in that function, in our function, we just have to plug in 0.5 there, and then if we do that, we are going to get f of 0.5, right, for this guy here, which is going to be equal to 0.5 to the power 3 minus 4 multiplied by 0.5 to the power 2 plus 1. And we get a value of 0.125. So now we have to find the first derivative of f of x, right? So if we have x here and we also have an x on this point here, so meaning our formula or our equation or our function is going to be x to the power 3 minus 4 multiplied by x to the power 2 plus 1 here, right? And finding the derivative of this function, we're going to have something like 3x squared minus 8x. And if we plug in 0.5 into this function, we're going to get 0.5, 3 multiplied by 0.5 squared minus 8 multiplied by 0.5. And our value is going to be negative 3.25. So now that we've found f of 0.5 and f prime of 0.5, then we can now plug into this equation now. And then we say P1 is equal to 0.5 minus this value divided by this value, and we have 0.53846, right? Great. So basically, that's how you solve Newton's-Raphson's method. You first get this value here, you have this function, and you have to find f prime of the polynomial and f of the polynomial you already have, and then you create an arbitrary value, or maybe let's just say they give you what x naught really is 0.5. So you plug in this value here, and then you plug in every value. So all you have to find is just f of x naught or f of p naught and f prime of p naught, and then if you want to find the first Newton's polynomial, then you say that and it will give you that answer, right? Okay, so only stop finding the iterations when Pn plus 1 minus Pn is less than or equal to your tolerance. So you continue doing this and continue doing this until the value, the absolute value of the Pn plus 1 minus Pn minus 1 is less than or equal to your tolerance, right? So we found our initial value, which is P naught, is 0.5, and we found P1, which is 0.53846, right? For our f of x, which is x cubed minus f of x squared plus 1, and then our f prime of x, which is 3x squared minus x. And we have our function, obviously, which is that guy there. So if we were to find P2, what are we going to do? Finding P2 here, meaning we're going to say P1 minus f of P1 divided by f prime of P1. So the value of P1 there, you plug it in those scenarios, and we have type of relationship, and we have 0.5374, and then we add it there. So basically, this is how you solve for Newton-Raphson's method. To find P3, just get this value that you found in P2, plug it in the formula, you find it. Really easy and very fast compared to a bisection where you have all these processes and everything. Actually, the reason Newton's-Raphson method was created was to simplify the bisection process. So you use this formula here and you solve this equation. So as an exercise, I'm just going to give you or allow you to solve for the remaining slots that are in here. Alright, so next up, we're going to talk about the secant method. And the secant method here is a slight modification to Newton's method. And the definition of the first derivative is used to replace the derivative in the Newton's method, and this leads to the formula Pn is equal to Pn minus 1 minus f of Pn multiplied by Pn minus Pn minus 1 divided by the same thing, right? Or f of Pn minus 1. So here there's a difference. There's Pn Pn minus f of Pn minus 1. So we have this formula, and it's a slight variation to the Newton's method. In the Newton's method, we had Pn. In this case, we have Pn minus 1, and then we have multiple multiplication and division entities on this point here. The secant method was used or was brought up specifically to combat problem of um, the problem of finding a derivative, because majority of the time with numerical analysis you're going to have functions that are basically cosine, tangent, sine, um, cotangent, and secant, and all these other methods. And majority of the time, you have a difficulty solving these equations, right? Finding the derivative and all that. So the secant method was used to, or was created to combat this actual problem. So notice that we don't have any derivative term in this um, sequence because we are not trying to find any derivative. It's trying to combat that drawback of Newton's method. So it eliminates the drawback of the Newton's method, which requires you to know the derivative of a function, like I explained earlier on. And it is also very fast compared to bisection, right? So it works by using the secant line rather than the tangent line. And here's a visual representation of how secant method works. Suppose we have a function or a function in this manner, right? And then we have x naught at that point, and we also have x1 at that point as well. So what's going to happen is we're going to have a secant line that connects this line from this line, or this line with this line rather, and then we're going to have that type of relationship there. And then on the x-axis, or on this line here, right, on the x-axis where this line crosses on the x-axis, we're going to have a point x2, right, and then we're going to graph that there. So our new point is going to be x1 and x2 there, right? And then once we have that graph, we're going to make another secant line, and then wherever this secant line touches the x-axis, we're going to have our next point, which is x3, and then we're going to keep on going as much as possible, and until we get to a particular tolerance. So this is how graphically secant method works. It works by using the secant line for bisection. Ironic, but yeah. So it uses the secant line for bisection rather than the bisection method, which uses the midpoint or the tangent line. Okay, so let's try finding the square root of 2 using the secant method, right? Okay, so we have our formula here, Pn, which approximates Pn minus 1, and our formula there. And in step 1, we find the uniqueness of the root in the function. So we already know that our function is unique in the interval 1, 2. So we're going to say f of 1 is equal to that, and then f of 2 is also equal to that. And then, therefore, f of x crosses the x-axis at least once within this equation. Right? Good. So we find two arbitrary values within the interval 1, 2. So rather than using one arbitrary value, we're using two arbitrary values. Right? So P naught is going to be equal to 1.5 within the interval, and then P1, let's just say something less, which is 1.45. Great. So if we have P naught, right? If we have P naught there, and then we have P1, then the values of P naught are 1.5, and we have P1 is equal to 1.45, right? Note to self that f of x is equal to x squared minus 2, which is equivalent to the square root of 2, which is equal to 1.4142, right? Stay with me now. We're going to say, using the equation there, and we plug in our values. So let's say P2 minus P2 is approximating P1 minus f of P1 multiplied by P1 minus P0, right? 1 minus 1 equal to 0. And then when we substitute all these values here, we got 1.5 and 1.45, you are going to get this type of relationship here. So you got in this function here, wherever x is, you just plug in those values, and we have 1.45 squared for this guy minus 2, and we have this equation. And if you do your calculations correctly, you are going to get something like this. You're going to get 1.5 minus 0.03475. And now when you subtract this value, you're going to get 1.4152. So notice that we're going from 1.5 and 1.45, and then now we're going from 1.4152. So meaning we are decreasing the value, right? And then we have 1.4152. Great. So now let's try finding P3. So now we found P2, and then we're going to say P2 and P1 there. Repeat the same process, and you're going to have P2, which approximates 1.4142. And then we can plug that in there. Notice that the secant method is way faster, and it is way more precise compared to Newton's method and bisection method. Whereas bisection method was dancing around the actual value, secant method actually approximated the actual value to 4 decimal places with very few iterations, which is very impressive for a method. So these are the 3 types of iterations that you can use to these are the 3 types of methods, that you can use to find solutions to equations in one variable. And we have, as we can see, that for bisection, we needed to have this table, and we needed to find here on the 6th iteration 1.41406. When you round this off, it's going to be 1.4101, and this was going to be 1.4179, and we were dancing around the actual value of the value of the square root of 2, whereas secant method actually got straight to the point on the 4th iteration. So that's actually very impressive if you ask me, honestly. So that's solutions to functions in one variable, or solutions to equations in one variable. That's bisection, secant method, and Newton-Raphson's method. Hope this video helps you understand the difference between the 3 and how easy the secant method is, how easy the Newton's method is, and how to be able to perform the bisection method of any function. If you have any questions or any queries, please feel free to reach out to me, and I will get to you as soon as possible. Thanks for watching, and have a great day.